Salam, Ajay, how are you? You okay, Ajay? Ajay, can you hear me?
Yeah, I can now.
How are you okay?
Sorry, I was.
Okay, that's fine. So we're just starting our lesson by reading over our notes. Is that okay?
Yeah, okay.
Okay, have a little quick read and then see if you're okay with that. Absolutely. Sometimes, guys, my plug gets pulled out. So if the computer turns off all of a sudden, what you'll find is I'll send you a new link in your emails. And then you just go in, and within 10 minutes of it turning off, you'll be able to find a new link and link onto that. It just happens sometimes. It's really annoying because my foot hits the charger or something. Huzaifa's arrived. Marco, have you read through the notes yet? You still reading?
I've read through them, yeah.
Oh, okay, cool. Yeah, Yasser, have you read through them?
I'm still doing it.
Still doing it? Okay, let's take a few more seconds. Ajah's still reading. Maybe Ajah might have read through it. Ajah, have you read through it?
Yeah.
Excellent. Okay, so whilst you guys finish off reading, Huzaifa, welcome. We're just reading through our last week's notes as a revision exercise. But now we'll start shortly on the lesson. Let me just take this bit here off. Okay, so Ahima's here as well. Okay, everyone's here. Right. So what we're going to do is we're going to go into the lesson. You guys can still carry on reading your notes and finish up on them. And we'll move into lesson very, very shortly. Hello, Ahima, you okay?
Yeah.
Good. Have you been reading through last week's notes on what we've done in waves?
I just joined.
No problem. All right. So what we've been doing so far, you haven't missed much because we've just been reading through our notes and recapping, yeah? So after the lesson in your own time, you can read through and just recap. Is that okay?
Yeah.
Okay. So we are on waves, guys, and we are on this journey looking through the different types of waves, their behavior, what they look like, labeling the waves, wave equations, how waves behave in terms of refraction, reflection, diffraction. There's a lot of things we've been looking at. And the reason, this is the main reason why we always recap before we start the lesson, just to go over all of this multitude of knowledge that we have. Because there's so much there, your brain needs to keep revisiting it. Right. So we looked at waves, we looked at transverse versus longitudinal, what the differences are between them. Okay. We looked at amplitude, wavelength, and frequency and their definitions. We looked at the wave equation and how we can use it to work things out. We understood that there were two wave equations we could use, which is this one, and also this little one here that's hidden, f equals 1 over t, frequency equals 1 over the time period. The time period is the time taken for one entire wavelength to be created or to exist or to move past a point. Whichever way you want to call it, the time period is the time taken for one entire wavelength. Okay, now we answered some questions. We looked at some different types of questions. So we used both equations to answer these questions. There are some experiments we're going to look at some point. We understood that wave fronts were the top of waves. So if you have a wave and you look at it from the top, you're looking at the amplitude bits, and that's known as the wave front. And therefore, this wave coming towards the coast can be represented using this straight line. The dotted lines represent the top of the wave. Okay. If my voice cuts up or anything, just let me know. I will be happy, more than happy to repeat what I say. Okay, we also said that when a wave hits the boundary, reflection can happen. Bending, refraction can happen, especially if the wave can go through it, if it's transmissible. And when it comes out, it goes back to its original angle. And also absorption, the wave can be absorbed inside the material. Okay. We said whenever a wave goes into a material that's heavier or lighter than itself, one thing never changes, the frequency never changes. The speed or the velocity in physics and the wavelength might. So we have to remember that. Reflection, we talked about the angle of incidence between the incident ray and the normal, and the angle of reflection between the reflected ray and the normal. If any of these words that I'm using, these keywords, are confusing, or if you don't remember them, feel free to ask, okay? We said that. Sound waves, we're going to go into that in more detail, as promised at some point during this journey into waves. With sound waves, we're going to look at ultrasound and other things. That's all going to come soon. But we skipped that, and we skipped that in favor of going to the next important bit, which was the electromagnetic spectrum. Now, the electromagnetic spectrum is a family of waves that all travel at the speed of light, okay? Electromagnetic radiation are examples of these waves. Visible light is one of them. Any light that you can see is an example of electromagnetic radiation. But there are other invisible waves that are also traveling at the speed of light. Amongst them are X-rays. Amongst them are ultraviolet rays. Amongst them is infrared, or the heat that we find in our lives. These all travel at the speed of light. Now, this is why if a bomb lands, a nuclear bomb lands 10 miles away, you will not be able to outrun the heat from it. The heat from it will travel at the speed of light, and it will melt things before they can get away from it, which is why one of the reasons why a nuclear bomb is so dangerous. Another story for another time. Okay, we said gamma rays, X-rays, ultraviolet rays, all of these rays or these waves are part of the electromagnetic spectrum. We said as you go from left to right, the wavelength increases and the frequency decreases. On the left, high frequency, low wavelength. On the right, low frequency, high wavelength. Now, this is important for biology as well, because in A-level biology, this is one of the reasons people like Josefa might be here as well. It's a recap of physics, and in A-level biology, you'll be looking at imaging, medical imaging, when waves are used in medicine. And so these waves over here in the spectrum are very important in medicine. For example, X-rays are important to view things in the human body. Gamma rays are important in cancer medicine to kill cancer cells. And there's many other examples which we can look at. Right, so we know what happens when a wave hits a boundary. We've talked about that a lot. We've looked at refraction. We explained last week how a prism works and how it bends different types of light to different amounts. If your light has a longer wavelength, it's bent less. If it has a shorter wavelength, it's bent more. This is why white light, which is made up of all of these different colors, a prism is beautiful in separating it, because it will take the red part and say, you know what, you just bend this much. It will take the blue part and say, you know what, you have a shorter wavelength, you need to bend much more. And because a prism bends light to different amounts, you're separating all the colors. We said a raindrop is like a prism because it does the same thing. Light moves from the air, sunlight moves from the air, which is light or which is less dense than rain, into a raindrop. So what the raindrop will do, it will function just like a prism does. In a way, the raindrop is even shaped a bit like a prism. It comes out, gets thicker at the bottom and gets thin at the top, a bit like a teardrop, okay? Right, so we said refraction happens through a glass block. You're bending the light. If the light enters at an angle to the normal, when it goes in, it will bend towards the normal. Yeah, this angle here of refraction, as it comes out, will be the same angle it comes out at. Interestingly, the same angle it goes in at over here, this angle over here will be equivalent or the same as the angle it comes out at. Another interesting fact is if you aim light down the normal or perpendicular to the object, perpendicular at 90 degrees to the object that you're going into, it will go straight through. It will slow down a little bit, but it won't change its angle. Okay, we took notes on all of that. So this is my recap for you guys because it's important, yeah? Using radio waves, we said radio waves can carry information, and therefore you can carry information and send it to a radio, which can then take that information and turn it into sound. A lot of things. Let me make sure you're all here still. Yes, you all are. Okay, two sources of radiation we said. The sun releases heat a type of radiation. Atoms, which contain a nucleus, which you've all gone through with me. You all understand what a nucleus is, hopefully. It's the center of an atom. That can release what we call nuclear radiation. Nuclear, why? Because it's from the nucleus. And nuclear radiation can be of different types, which we'll learn about at some point. Some of you are already doing radioactivity with me, so you know what it is. So now we spoke about that. A nucleus loves to release radiation. Harmful radiation, we said, radiation can kill you. Some types of radiation can damage your cells. So when you're working in a factory or somewhere that involves radiation, in the UK, you have to wear what we call a dosimeter to measure your radiation dose. And in America, where The Simpsons comes from as well. Okay? You're measuring your radiation dose, how much you're getting, in a unit called sieverts. Just like we measure mass in kilograms or force in newtons, we measure radiation in a unit called sieverts. Okay. Now, excuse me. There's different types of radiation. Gamma radiation is an example of a harmful radiation. It can cause cancer. It can cause your blood cells to mutate or damage. It can damage the DNA in your cell. And when that happens, the cells become cancerous. X-rays can also do the same thing. Ultraviolet can also do the same thing. The interesting thing is these can also benefit you. X-rays can be used to look at your bones and help doctors fix problems in your body. Gamma radiation can cause the mutation of cells, but it can also kill cancer cells. Interesting. Ultraviolet can help you to get a tan, but it can also kill you. So again, problems. Now, UV radiation, we looked at this page. We looked at radio waves, reflecting them off the atmosphere. Let's say there's a mountain and Marco wants to send me a signal. Marco can aim it at the sky, it can reflect and it can come to me. And then I can try to communicate using that. I have a mobile phone, but I want to watch Netflix from America, let's say. Netflix will send a signal to a satellite, microwave. That signal will then come to my phone, and then I can watch what's going on. Right. So infrared we talked about as well. We talked about all of this. We took this table down. And this recap has been quite long, but it's very important, I think, yeah? We looked at lenses, how they bend light. And we looked at prism, how it splits light. We looked at converging lenses and diverging lenses. Converging lens, what it does, it brings light together. It converges it to what we call a focus. A diverging lens spreads light out, yeah? So there's different things that lenses do. We looked at ray diagrams, which is very important. Look what the converging lens does to the light. It bends it towards a focus. We said the distance between the middle of the lens and the focus is called a focal length, okay? So that's the focal length. We talked about virtual and real images, which we'll go into more detail later. But we then said a diverging lens brings light together at a focus. Oh, sorry, spread light out, my bad, just confusing my words. The interesting thing is here, when a diverging lens spreads white light out, the light rays that are spread out, if you trace what direction they should come from, so if I carry on going back from this ray here, and I carry on going back from this ray over there, carry on going back from this one, carry on going back from this one, they all meet at a point. And that point which they're supposed to meet at is called your focal point, or a diverging lens, or your focus. And the distance between that and the middle of the lens is called your focal length, as you can see there. Okay, so there's a lot we covered. We then ran into magnification. We done some equations on it. Right, now, so we're going to the next bit. So guys, now that we've recapped, what we're doing is we're going to start looking at what we call visible light. I want you guys to write the title down, visible light, and we're going to mention an important point that we were discussing earlier, okay? Visible light is your title. If my computer suddenly turns off because my plug is being very funny, just know that you can come back on in 5 minutes or 10 minutes after it turns off, go to your emails, click on the new link, yes? Just sometimes, sorry about that. It's just a bit of an inconvenience that we have to live with suddenly. So visible light, white light, okay? Spreads into all these different colors. What we find is visible light exists in a spectrum. So you've got reddish to yellowish to bluish. So you've got reddish to yellowish to bluish, yeah? Same kind of thing. Now, what we need to understand is red light has a wavelength that's longer than blue light. And we spoke about this. So red light, the wavelength is very small, 0.000007 meters. As we get towards blue light, we find it's even smaller, even shorter. So what I want you guys to write is the following sentence after visible light. I'm gonna write it here. In the visible light spectrum, and I think you can all see my page, hopefully. As we go from red to blue, the wavelength shortens. The wavelength shortens, and whenever wavelength shortens, something else increases in light, which is the frequency. The wavelength shortens and the frequency increases. So write this down, guys. Frequency increases. Okay. Can you understand my handwriting, Marco?
What's the third word?
Visible.
Oh.
Yeah, good. Yeah, just let me know because I'm just writing out. Light spectrum. That's spectrum there. As we go from red to blue, the wavelength shortens and the frequency increases. I'm going to start writing in separate letters. It's better, I think. And I always say that, and I need to start doing it more often. Now, we know when the longer wavelengths go through a prism or go through something thicker, they're going to be bent more, or sorry, less. The longer wavelengths get bent less, as you can see in the diagram. So some of you are copying, some of you can start looking at it further here. You see this red light doesn't bend as much. The shorter the wavelength, which is blue light, for example, it bends more. This is a very important fact. Okay, it's one that I want you guys to remember. Okay. Have you written that down, Audrey?
Yeah.
Okay, good. Have you finished writing it, Marco?
I'm on the last line.
Last slide, okay. I'll give you guys 10 more seconds. And if you need more, just let me know, yeah? So if I switch it up and you guys need more time, either you can put your hand up or just say, sir, can you give me a second? And don't worry, you can use that. Okay. Right, so now we're gonna look at this. Again, tell me if you need more time. Right, so what happens when this light hits a material? There's 4 possibilities that can happen, yeah, when light hits a material. Absorption, the material can absorb it. Transmission, it can go straight through. Reflection. Reflection is an interesting one. It's like men and women, divided into 2 categories. You can have diffuse reflection and specular reflection. We're going to talk about this. You guys already know what absorption is. I don't think we need to talk about that. And transmission. Transmission means you go straight through. We can ignore that if you need to. Absorption is when it can't go through. Yeah, it's absorbed. It just goes into it. Wood might be an example, not the best example. Thick glass might be a good example. Very thick glass, light goes in and it can't come out. A mirror will do what we call, so absorption goes there. A mirror is important, and also a surface that's very rough. This is like a mirror and a piece of tin foil. If you look at kitchen foil, it's just like a mirror, but kitchen foil has rough edges on it. And a kitchen foil bends and a mirror stays straight. A mirror is quite smooth, a kitchen foil bends up in different directions and has rough edges. So they both reflect light in a different way. When you look at your face in a mirror, it's nice and clear. When you look at your face in a kitchen foil, very blurry. So what we call this type of reflection is specular. A mirror, and you can write this down, you can show the reflection in a mirror. A mirror will cause specular reflection. What does that mean? The angle of incidence is equal to the angle of reflection. And we'll write some stuff about this. But a surface which is not even will do what we call diffuse reflection. The angle of reflection is not equal to the angle it goes in at. So I want you guys to write this down. There are 2 types of reflection, specular and diffuse. Specular, angle of incidence equals angle of reflection. Diffuse, angle of incidence doesn't equal angle of reflection. As you write it, you can ask me to repeat it as well. Sometimes I'll dictate notes to you just to get your dictating skills up or your listening skills up, but you can ask me if you forget. So remember, you're talking about the two types of reflection: specular on a smooth surface like a mirror. The angle of incidence, the angle the light goes in at, is equal to the angle of reflection. Diffuse on a rough surface, let's say, the angle of incidence is not equal to the angle of reflection. And when you're designing a mirror, this is the type of reflection you want. The best mirrors have these angles equal. They're very, very smooth. Because when a mirror is not smooth, what it does, it throws off the reflected light. So smooth mirrors cost, if you want to get a mirror really, really smooth, it's a really long, expensive, and very meticulous process. A smooth mirror that's good, that's at a very high level, can cost tens of thousands of pounds. Yeah. Whereas a normal cheap mirror, it will do the job, but it won't do it as well. Okay, I'm going to move on. Okay. Now filters. Now tell me if I move on and you need time, tell me. I'm doing it a bit different today, so just let me know. Right. Now a filter is something that can block out certain types of light. It's very interesting how that works. So I'm going to skip some pages, which I don't even want right now. So imagine you've got white light, and you know white light is made up of different colors. So white light's coming towards you. All of these different colors are coming towards you. You're wearing sunglasses, or you have a piece of plastic made of red. What are you going to see on the other side of that? If I have a red filter and I'm looking through it, a red piece of plastic, even if I aim it at the sun, on the other side of it, I'm only going to see red. So what it does, it absorbs all of the other types of light. If I have a magenta filter, or purple, or royal blue, some people call these different colors, it's going to absorb everything except for magenta and a few others, yeah? And they're going to come through, and you're going to see them. So these colors, red, blue, and purple, make up magenta, to be honest. I'll be a bit more accurate with my words with colors. So what you need to understand, you can write this on filters as a title. The color of a filter will block out every other color of light. So you can say a filter will block out every type of color except its own. A filter will absorb, so write filters, and underneath it, a filter will absorb every color except its own. I'll write that down in notes if you want. So underneath the title of filters, you'll write a filter will absorb every color except its own. Okay. So if they ever give you a filter and they ask you, what would you see on the other side of this? Usually you'll say the same color as the filter. If they give you magenta, for example, which is a bit more involved, you could say, at the least, I'll see magenta on the other side. On a more advanced level, you realize that magenta is a mixture of colors. So we'll only allow the colors through that can mix together to give it. Does that make sense, Ahima?
Yeah.
Excellent. Right. And if it doesn't make sense to anyone, just tell me. I'll ask random students sometimes just to confirm. Okay. Random meaning any one of you. I'll just pick randomly. Okay. Now that we've done that, we can move to the next part. So, seeing color. Now, if I see a book and it looks red, it does the same thing as a filter in a way, yeah? But it reflects it. So a book that's red, all of the colors of white light will fall on it. If this book is outside in the sunlight in a park somewhere, for example, or we're just reading it in our room with the lights on, what the light will do that we're using, the light will hit the book. And the white light that hits the book, being made up of different colors, the book will absorb everything. It will reflect red. And that's why we'll see it as red. If you look at a purple pair of trousers, which is weird for a boy, okay, right, what will happen, it will take every color except those that make up purple, yeah? And sometimes it might reflect another one. So purple, this purple trouser might have a bit of red in it. They might have put some red dye in it as well, so it'll reflect some of the red as well. If you look at white and purple, and for example, blue, yeah? If you look at white, for example, what do you think will happen here, Yasser? What will a white hat do? What will it reflect? Go on, Yasser.
Will it reflect all of them?
Yes, because it's white, so it reflect all of them. Yeah. So we've got to understand that if we look at a football kit, for example, you're gonna have different things going on. The top might just reflect red, and the bottom might just reflect the blue. Everything else will be absorbed. So what you're learning from this, guys, is that color reflection is very important, and we need to understand what's actually going on. So before we move on to this next bit, I want you guys to summarize what you've learned here. So in your own words, I'm not going to say anything. In your own words, talk about reflection. I'll give you a title, Reflection of White Light. And in your own words, I want you to write about what's going on with the reflection of white light. Use some examples. And I could have made this a 6 marker, but I won't. We'll do a different exercise here. Just write down the reflection of white light as your title and explain what's happening when white light is reflected. Let's say it reflects off something red or blue. Give examples and say what's happening to the light. I'll leave a bit of information here on the side for you guys to write from. As soon as you're finished, let me know. Any of you that have finished writing, let me know, please. Don't be shy. As soon as any of you write, just say done. So Huzaifa, tell me what you've written. Can you hear me, Huzaifa? I think Huzaifa might have gone to the bathroom, that's fine. Let's ask, who haven't I asked a question yet today? Let's see who's on my list. I've asked Mark, I've asked Yasser, I've asked Huzaifa, I've asked Ajur. Let's go back to Ahima for now. So Ahima, what have you written? Tell us.
I haven't written anything yet.
No problem. You're thinking about it?
Yeah.
Okay. Do you understand what's going on? Like, do you know what to write?
Like, do I write like things that I know about white light?
Like the things that we've just learned about here. So for example, I'm going to give you an example in a second. I'm going to ask someone else and we're going to use them to help give you an example, yeah? Let's ask Ajur. What have you written, Ajur?
White light contains all the wavelengths of the visible spectrum. So when white light hits a surface, it is reflected, meaning it is reflected of the wavelengths of visible light equally.
Okay, good. So I'm going to start adding to your answers here, guys, yeah? So white light contains, and I'm going to write it, those were good answers. So let's write here over here, for example. So white light, I'm going to write in red today, don't know why. White light made up of different colors. Made up of different colors. So you guys write this. I'm going to try and write it separate a bit. Different colors with different wavelengths. Okay. So that was good with different wavelengths. Now, it can be reflected differently off different materials. So these colors are reflected or absorbed by materials. Reflected or absorbed by materials. Okay, I'm gonna make this a bit bigger. Okay, now let's change the color a little bit. So that's wrong colors. So what happens? The different colors with different wavelengths we can write as Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That's just the way to remember it. It's not essential, just I'm putting it there for now. Now, if the light is shone, if you shine it on a surface of a particular color, what would it do? That surface will absorb all of the colors except its own. Absorb, and this is, you can write this in the phrase, absorb all of the colors, all of the wavelengths, or all of the colors, except, this is a big exception, its own. What will it do to its own one? Which it will reflect. Which it will reflect. Okay, so what does that mean? For example, thus, or for example, a red jacket will absorb. Generally, this is what will happen. I'm going to write the acronyms here. Orange, yellow, oopsie daisy, green, blue, indigo, violet, and reflect red. And this is why making it appear to be red. Appear to be red. Now, as soon as you guys write that down, you let me know. Okay. As soon as you write, guys, let me know. I'll give you guys another 20 seconds and I'll ask if you're okay and we can move on. I smell food. Okay. Which one are you on, Marco? Which line?
The third,
To last.
if the, yeah.
Okay, fine. Whereabouts are you, Ajay?
I finished before you.
Okay, cool. Well done. I think Ajay should teach us lessons. Good. Well done. Ahima, which one are you on?
I'm on like the third.
Perfect. And Yasser? That's good.
I'm on the last one.
Last one. And Huzaifa?
Third one.
Okay, cool. So, Ajay, you've got a test tomorrow, I believe, right?
Yeah.
How's the revision going? While these guys copy, we can make some use of this time. How's your revision going? Is there anything that you're stuck on?
No.
Okay, good. What's the test on again? I forget.
Radioactivity.
There it is. Okay, good. You're going to be okay. Have you finished all the exam pro questions?
Yeah.
Okay. What you can do, since you finished them, is if you want, you can go on there and get new ones off, because there'll be new ones. There's a lot that I haven't put on that onto that exam paper, because there's a limit on it. So you can go on there and look at that if you want and do extra questions, or you can just. I don't say this lightly. You can relax if you need to, because you've done a lot. Sometimes it's good to relax before an exam. But yeah, it's up to you. Read through the notes, just go over it again. You'll be okay, hopefully. And give me a shout if you need any extra help. Okay, so guys, if you give me permission, I will move on in the next 5 seconds, okay? And if not, what I'll do, I'll leave this on a little bit over here, and we'll start talking about the next bit of what we're doing here. So I think you're all on the third one at least. So I'm going to bring this down here. Okay, just going to bring this down here. Right, and bring this a little bit over to here. Makes it disappear, that's fine. Right, so let's minimize this if you guys are ready. Anyone not ready for me to move on? Okay, don't be shy if you're not ready. There's no need to be embarrassed or shy. It's okay, because I'll always give extra time in the lesson if we need. If I feel we're wasting too much time copying, I'll give extra time to you guys, so no one's going to lose out. All right, so good. Let's move on, since no one's saying they want me to keep on here. Right, so you have to understand now, or you do understand now, that something of a particular color will absorb everything except the color it's made of. Sometimes the color that something is made of is a mixture of different colors, so it will absorb everything except that mixture, and it will reflect the mixture. Now, white is a mixture of all the colors of white light, so it will reflect every color, okay? Now, sometimes, an interesting point is using colored light. If I use, let's move on here. If I use just red light, an interesting thing happens. Because red objects reflect red light, the red light's going to come off of it. But over here, what's going to happen, guys? This is not red. It's not the same color as what's coming in. Whenever two things are of a different color, it's absorbed. So that shirt part there looks red. Here, the red light will get absorbed. And this part, the shorts, will look black because nothing's coming out. So guys, I want you to make a note of that. Whenever you have, and I'll write down actually, because, you know, it might get a bit confused if it's not written. Now, I'm going to rub this page out, or I'm going to rub the top out. Okay, let me get the eraser here. Make it big. And this top bit, I just want you to realize it comes after this bottom bit here. Okay, so we know what we just learned a minute ago was that an object will absorb every color except itself, which will reflect. So for example, you don't have to copy this right now. Let's say I've got blue, yeah? Blue light, maybe blue light or something. And the object is made of something that's blue.